Well, okay, this reading is on sampling and estimation as we continue our journey through quantitative methods applications. And this is going to lead into hypothesis testing next. So we're going to lay the groundwork for that and talk about some taking a sample from a population and then estimating some parameters of the population and making some probabilistic statements about the underlying distribution from that. So as usual, let's get some terminology down first and then we can run with it. To make inferences about the parameters of a population, we'll use a sample. And a simple random sample is one where every population member has an equal chance of being selected. I'll give you a quick example of a non-random sample and how it came about. Back when I think it was the Gallup polling organization, which were some of the earliest ones in polling, they would send their people out and say, well, we want to sample one resident from each block, each city block. Well, if you have to hit one house on each block, what's the easiest way to do that? Well, they would go to the corners, right? And then they could hit 4 houses from that location, one on each block, cover 4 blocks, and then move down to the next 2 intersections down and do it again. And so this is the way they were doing it. Well, it turns out that people with corner lots in the city, often those are larger, more expensive houses, sometimes with more frontage, they'd be paying more taxes and things like this. So they were getting a biased sample from each block by using just the corner houses. So they had to go where they actually would choose addresses at random out of the whole pool because they weren't getting a simple random sample. And we'll talk about other types of bias here as we move through, sampling bias. A sampling distribution, this is an important point. We're going to have to use this. The sampling distribution gives us the distribution of the sample statistics for repeated samples of size n. Well, let me clarify that a little, or expand on it a little, and say we've got we want to estimate the mean. Say we've got a large barrel full of ping pong balls, all with numbers written on them, and we want to use a sample to estimate what's the mean value of all the balls in the barrel. We can't count them all. We're not going to count them all. So this sampling distribution says, let's say we decide our size n is 20. So we're going to take a sample of 20. We're going to take those balls. We're going to add up all the numbers and divide by 20. That's our sample mean. Well, this sample mean is going to be different every time we take a new sample. Or at least it can be. So if we do this 100 times and we plot out all the different sample means for these samples of size 20, that distribution is the sampling distribution. And we'll see under certain circumstances that sampling distribution actually has the same mean as the whole population. And we can make probabilistic statements about how confident we are that the true mean of the distribution is within some interval or another based on our sampling. So that's how we're getting to sampling and estimation. And the last term on this slide we need is sampling error. And that's just the difference between our sample mean, or some sample we estimate any parameter with, but certainly for a sample mean, how far is it from the true population mean? That's our sampling error. The difference between the sample mean and the true mean when our sampling is to generate a sample mean. Now, as opposed to simple random sampling, we've got stratified random sampling. The idea of stratified random sampling is to preserve certain characteristics of the whole population in your sample. And the easiest way to understand this, and really the reason that it's introduced, is sometimes in trying to match an index portfolio, especially bond indexes. Okay? They don't just match it. I mean, if you want to match the S&P 500 stock index, that's pretty easy. You buy all 500 stocks. They're all liquid. They trade readily, and you can match up the weights that you need, how much of each stock. So they can just match that portfolio. But with bond portfolios, it's much more difficult. You've got liquidity issues. You've got costs of buying and selling that can distort things. And so often they'll use a sampling technique to get a portfolio that attempts to match the performance of the overall bond index. So we haven't been introduced to a lot of these things yet, these characteristics that bonds might have. Okay? But let's talk about them and not worry too much about them, and we'll learn much more about them in fixed income. Let's say we've got this bond index, and some of the bonds are callable and some are not. Some are long maturity, some are short maturity. Some are quite risky, like junk bonds, and some are not risky. And we could talk about 4 or 5 important characteristics of these components, these bonds in the bond index. So in order to do stratified random sampling, we're going to say, well, let's take a box here, and let's label that box callable, short-term, high credit quality corporate issuer. And all the bonds that fit all of those characteristics, we throw them in that box, bonds from the index. And we follow this, and now we've got these bonds divided up into all these subgroups, and each subgroup, they are very similar in what we consider the important risk characteristics. Then we do our random sampling from each box. So if there's 30 bonds in this box, and we say, well, we're going to take 10 of those as our sample, or 8, or whatever. So we take a sample from that subgroup, and then we buy those bonds in proportion to the size of the subgroup. So if the bonds in that box represent 12% of the index, we invest 12% of our portfolio in those bonds we selected randomly from that box, from that subgroup. And what does this do? This preserves the characteristics. So it says, well, you're going to select randomly, but we know 12% of our portfolio is going to be bonds with these characteristics. 8% is going to be bonds with these characteristics. So we've done the random sampling, but preserved the characteristics of the overall portfolio in terms of what we consider to be the important characteristics or risk factors that we're interested in. Time series versus cross-sectional data. Well, this is an easy learning outcome statement. Time series data goes across time. Monthly prices for IBM stock for 5 years is time series data. When we talk about cross-sectional, we talk about a certain period in time and look across industries or across companies or across different securities, things like this. Now, sometimes we'll use both. We'll have data that is both time series and cross-sectional, but many times we'll define a test or a study that we're doing as being based on time series data or based on a cross-sectional analysis across firms, industry, means, things like that. Okay, this one's important, central limit theorem. The central limit theorem is what's going to allow us to make some probabilistic statements and do hypothesis tests here in the material we have left in quantitative methods. And importantly, what this says, it says, okay, let's go back to our big barrel full of balls with numbers on them, ping pong balls with numbers carefully written on them, thousands and thousands of them. It's a big barrel. Okay. And the central limits theorem says, well, no matter what the underlying distribution, no matter what that population is, as long as it has mean mu, a finite mean, and a known or finite variance, sigma squared, as the size of our random sample gets large, the distribution of sample means approaches a normal distribution. With mean mu, that is, our sampling distribution has the same mean as the underlying population, and its variance is sigma squared over n being the sample size. So a couple of things come out of this. One, even if we don't know the distribution of that underlying population, once we start taking sample means, they will be approximately normally distributed, and we can use that standard normal, the z-table, and all that to talk about probabilities of being above this or below this or within this interval using normality. And that's very important. The other part, the variance of our sampling distribution, approaches the variance of the underlying population. So that's sigma squared. That's the variance of one draw, each individual observation in our population. Once we start taking a mean, if we take a mean of 10, the mean of sample size 10, we're going to get a better estimate of the mean, a tighter estimate to the mean than if we only chose 5 or only chose 1. And if we took sample size of 100, we'd start getting really pretty good guesses, pretty good estimates of the mean. So the variance of this sampling distribution around the true mean gets smaller and smaller as our sample size grows, and, not shockingly, the way it gets smaller is we divide it by n. Now, something we're going to run into in just a bit is the standard deviation. And so if we've got the variance of this, just remember, if I've got room to write here, if we take the square root of that variance over n, we get sigma over the square root of n. And so that's what we're going to run into when we start talking about the standard error, that is the distribution of sample means that depends on the sample size n. And so that's what we see here. Okay? When the population is known, population variance or standard deviation is known, then the standard error of the sample mean is what we're after. And so that's just the square root of sigma squared over n, sigma over square root of n. And when the population standard deviation is unknown, we use S, our estimate of the sample standard deviation. So that sigma and that S, that's the standard deviation of the underlying population. S over square root of n, that's the standard deviation of the sampling means around the true mean, but we call that the standard error. So use the standard error when we're trying to talk about sample means of size n. Use the standard deviation when we're talking about a single draw or a single observation for a random variable from the underlying population. So let's put this to work. The mean price-earnings ratio for a sample of 41 firms is 19, and the standard deviation of the population is 6.6. What is the standard error of the sample mean? Well, we've got 41 firms, so we're just going to take the standard deviation of the population and divide by the square root of n and get 1.03. And so our interpretation of that is that for samples of size 41, the distribution of sample means has a mean of 19, at least that's our best guess right now, and a standard deviation, which we're calling the standard error, of 1.03. So greater the sample size, this distribution collapses down tighter and tighter around the mean. How about some desirable estimator properties? You know, this is not a far-reaching learning outcome statement. It really stands on its own. You may get a question on it, you may not, but it's not that complicated. We've got 3 terms to remember here, and the first one is easy, unbiased. If we're estimating, and let's just talk about estimating the mean of a population of these balls in the barrel. And so the expected value is equal to the parameter we're after. Well, we know the expected value of the sample mean is the mean of the underlying population. Okay? And our sampling error is how far we are from that, but our expected sampling error is 0. So we've got an unbiased estimator. Even if you take just one ball from the barrel as your sample, it's still unbiased. Okay? It may be too high, it may be too low, but it's not predictably too high or predictably too low. And the expectation, if you just grab one at random, your best guess is the mean value. Now this second property, efficiency, it says the sampling distribution has the smallest variance of all unbiased estimators. Well, this isn't too hard to make sense out of. If we've got 2 unbiased estimators to choose from, The efficient one has the smallest variance of all of those. So if they're both unbiased, let's choose the one with the smallest variance. So far, so good. And consistency is just the property that if we increase the sample size, our estimator gets better. Well, clearly our sample mean matches all has all these desirable properties, right? We take a mean, sample mean is size 20. Its expected value is the same as the mean of the population. Okay? There is no other sampling distribution that has a smaller variance that is unbiased. And the larger our sample size, the better estimate of the true mean that we get. So maybe you can remember it in that context, is what are the desirable properties of an estimator? Well, what properties what properties does this sample mean have? And it does have all three of these properties. Okay, point estimates and confidence intervals. When we take a sample mean, that's an estimator of the population mean. And we're pretty sure it's not right on the nose, right? But it's unbiased. It's the best guess we have. It's the best estimator we have. Now, we can look at the distribution of sample means around the true mean and use that to establish a confidence interval and say, well, here's a range. We're 90% certain, or we're 95% certain that the true mean is between here and here. And so this is what I meant when I keep saying we can make probabilistic statements about the parameters. So we've got our point estimate. That's our guess at the value from taking our sample mean. Okay. But given the standard error, the dispersion of these sample means around the true mean, we can use that to say, well, 95% of the time, given what we've seen here, the true mean is going to be between here and here. So that's our confidence interval. And we can do that for 99% or 95, 90, whatever percentage is appropriate in the application. So the greater the variability of the random variable, the wider the confidence interval. Makes sense. If we have sample means from samples of size 5, our 95% confidence interval based on that information is going to be wider than if we had sample size of 100, or more sure we've got a lower standard error, and our confidence interval would be narrower. The larger the sample, the narrower the confidence interval. Okay, so we've talked a lot about the normal distribution. The student's t distribution is let's treat it as a variant of the normal distribution. It's got a parameter called degrees of freedom, and for all your level 1 stuff, degrees of freedom are always n minus 1. So that'll change a little at level 2, but we certainly don't have to worry about that yet. So degrees of freedom, n minus 1. And it's a mathematical, statistical concept, but think of it this way. If you've got n values, and I tell you n minus 1 of them, and the mean, you can figure out the other one. That's all that's going on here. So it says if you've got the mean, then you can only identify n minus 1 of the n values. The other one is determinate already because we know the mean. I don't know if you even need to know that, but it may help you remember it and make some sense out of it. So a student's t distribution has fatter tails than a normal distribution. And as the degrees of freedom increase, I'm down here at the bottom now, as degrees of freedom increase, the t distribution approaches the normal distribution. So if degrees of freedom, 200, something like that, it gets indistinguishable from the normal distribution. Okay. But when we have lower values, we've got these fat tails, we're going to need what? We're going to need wider confidence intervals, because if this distribution has fatter tails than the normal, if we want 90% interval, it's not going to be 1.645 standard deviations either side, because with fatter tails, we've got more probability on these extreme outcomes. So with a t distribution, we just need a wider confidence interval for 90% than we would under normality. And again, the greater the sample size n, the closer we are to the normal confidence interval, the confidence interval with a normal distribution of the underlying random variable. So here's a picture of that. Now don't be concerned with this center. There's some controversy over there. Remember when we saw a leptokurtic distribution, it was a little more peaked in the center. But for our purposes here, just focus on those fat tails. So we show an example of a T distribution with degrees of freedom equal to 1, and then one with degrees of freedom equal to 100, where we're getting pretty close to a normal distribution. And the reason we care about these fat tails in finance is often we use normality to make our probabilistic statements and confidence intervals and stuff, but if the distribution is non-normal and has fat tails, then we're underestimating the probability of extreme events, and we don't want to do that, especially on the downside. So that's why we care about these fat tails and the T distribution. Now, let's talk about constructing these confidence intervals. We've got a point estimate plus or minus what we'll call a reliability factor. That reliability factor, that's our 1.65, 1.96, depending on the percentage confidence we want on this interval. So a normal distribution with mu equals 3, mean 3, standard deviation 2, a 90% confidence interval is simply 3 plus 1.65 times 1.65 standard deviations, which is 2 here, or 3 minus 1.65 standard deviations. And that gives us a range from 0.3 to 6.3. Of course, the center of that range is our point estimate, okay, and the range gives us our confidence interval. For a 95% confidence interval, you want to be more confident that the true mean is within your interval. You got to make it a little wider, and so that's why we use 1.96 standard deviations rather than 1.65. Simple as that. I'm sure you've gotten that point pretty clearly by now. So now we've got this chart here. It looks a little daunting, but I think when we take it apart, we'll be fine. Let's start off with the Z statistic. We've got a Z here. It says we can use the Z here, and the reason is we know the variance. Okay. And we know the variance. When we don't know the variance, and most times we probably don't, I mean, who's going to tell us? So we have to estimate it. If we estimate that variance or standard deviation, that adds another little bit of uncertainty to our confidence interval, doesn't it? Because we're saying, okay, 95% confidence interval, let's go 1.96 standard deviations either side of our point estimate of the mean. But what if we're unsure about that standard deviation? In order to be sure we've got a 95% probability of being in that interval, got to make it a little bit wider. And what does it do when we use the T distribution? It's got fatter tails, depending on the degree of freedom, fatter tails than the normal, and we're going to have to use a little wider confidence interval, and that's accounting for the fact that we're guessing, that we're estimating the variance. But that said, if we have a large sample size, which we're just taking to be greater than 30, usually not a big problem. Some samples are smaller, but in many cases 30 is not a hard sample to get at all. It says we should use the T statistic when the variance is unknown and we've had to estimate it, but it tells us in the CFA curriculum that the Z statistic is theoretically acceptable here. Now, given computing power, I don't know why we'd want to use a Z statistic instead of a T statistic, but remember, we're preparing for the Level 1 CFA exam, so we just need to know what they want us to know. And so now we've said all of these, along with this, that's all the Z statistic. So now we're down to one instance where we must use a T statistic, and that's if we have a small sample and a normal distribution with an unknown variance. So when the variance is unknown, we showed up with a T statistic, but the only time we really have to use it if we have a sample less than 30 according to the CFA curriculum material. And what about these down here, this not available? Well, a non-normal distribution, that just means that it's not, we don't know that it's normal. Okay? It doesn't have to be identified as that. If we just say oh, we're looking at a distribution and blah, 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 you can take that as non-normal. If it's not identified as being normal, we don't know that it's normal for sure, it's non-normal. Well, if we don't know the distribution, if we don't know the probability distribution of the balls in the barrel, and we take a sample of less than 30 balls, it's not reliable at all. Whether we know the variance or not, we could have some real odd distribution in there, and our sample mean could have some odd properties, and we just don't know. So if you break the table down that way, you've got one to remember: small sample, unknown variance, normal distribution. We can use a t-statistic. Non-normal, small sample, we can't do a darn thing, and anytime we have a large sample, it's supposedly acceptable to use the z-statistic rather than relying on the t-statistic for some particular level of degrees of freedom. Let's take a look with the unknown variance. Sample mean is 19, sample standard deviation is 6.6, and n equals 41. Establish a 90% confidence interval for the population mean. Well, pretty straightforward here. Now, the reason we say the variance is unknown, notice in the wording here I have that the sample standard deviation is 6.6. If you see a problem where it says standard deviation is 6.6 or variance is such and such a number, you can take that as being the true variance. Unless it says sample, then it should be talking about the true variance, at least in the context of a problem. Establish our 90% confidence interval. Okay? Well, let's do this, even though we have 41. Let's just use that t-distribution here. Our t-reliability factor, if we look it up on the t-table, and you should familiarize yourself with the t-table just as you have with the standard normal cumulative distribution function table, so-called z-table. Take a look at that. Our degrees of freedom are just 41 minus 1, and sample size minus 1. Alpha over 2, that's how much probability is in each tail outside the confidence interval. We want a 90% confidence interval. That puts 5% in each tail, the negative tail and the positive tail. So the standard error of the mean, that's our 1.03. We divided our sample standard deviation by the square root of the sample size. And now we've got our confidence interval for the mean based on a t-distribution. One of the reasons I wanted to use the t-distribution here, even with 41 as our sample size, is to show you the only thing that's changed from what we did before is we have a larger reliability factor. If we knew this was normally distributed, we were using a z-table, then we would use this 1.65 for our 90% confidence interval. But because we've had to estimate the sample standard deviation, use the estimate of the sample standard deviation, we want a little wider confidence interval, and that's exactly what this little bit larger reliability factor does when we've applied it here in constructing our confidence interval. Sample size issues. So far we've talked as if sample size is just a wonderful thing, and there's no drawbacks, and we should get the largest sample size we possibly can. Well, that's why this learning outcome statement here, we want to talk about some of the trade-offs or drawbacks. So one of the trade-offs is cost. Cost can be a factor. Obtaining more data can increase cost. So there is a trade-off. And if you haven't done research, you may think, oh, well, you just go and get the data and it's all available. Well, no, sometimes we do studies, we do research where we have to hire people to go through the old newspaper headlines or something like that to find companies that have had different events and things like that, or see how companies have reacted to events in the news. Or sometimes it's just a very hands-on thing to get a larger sample size, and sometimes maybe the sample is just not out there, so the cost becomes prohibitive. So that's one of the trade-offs there. The other point is a little more subtle and has to do with probabilities. If we include more data points, but they're from a population or a time period with different mean and different standard deviation, then we're kind of polluting our sample. Rather than making our estimates better, we'd be making them worse. Think about some data, economic data or market data from pre-World War II and post-World War II. And to some extent, it looks like the parameters of some of these distributions changed markedly over those periods. So if we had done some research with post-World War II data and we said, well, we found some interesting results, why don't we just beef these results up before we go to publication? Let's grab some pre-World War II data and do the same thing. Well, that may give you more precise estimates if it's all from the same population, but if pre-World War II data has a different mean, a different standard deviation, different skewness, different kurtosis, any of that, then by adding that data together, we've actually put more variation in our results instead of making them more precise. So those are two issues to consider about sample size. Okay, some types of bias. We've got 5 types of bias here. The learning outcome statement, the command word here is describe. So data mining, that's repeatedly going back to the same data over and over. And let me tell you what can happen here. If we're going back and doing these tests and we're at 90% is our standard, or even 95, okay? What that 95 means is that 5 times out of 100, 5% of the time, what we said is going to be violated. So even if something is true, 5% of the time, your results are going to be out in one of those tails. And so if the same researcher does 100 tests, 5 of them, he's going to be outside those bounds just by chance, just randomly. And those may be the ones that get reported in the literature, right? If you don't find anything surprising, nobody wants you to write it up and send it in. If you find something and go, wow, this isn't supposed to happen, well, 5 times out of 100, it will happen if you're using that 5% significance, as we'll come to call it, or 95% confidence level. But it doesn't have to be a single researcher just going through the data until he finds something that stands out, and which could happen. You know, our standards are just not as high. If we do 100 tests, we know 5 of them are going to, on average, okay, give us unusual results. But it could be just 100 different people doing 100 different tests, going back to the same data. And what's that same data? The returns on stocks since 1926 that are in the databases that everybody's looking at. Okay, sample selection bias. We talked about that kind of bias. If the sample's not really random, you've got problems. Survivorship bias. Survivorship bias, I guess one way to think about this is especially important for hedge funds and mutual funds. But think about if I wanted to do a test on whether smoking caused death and lung cancer. I just wasn't convinced yet from the existing data. So I say, well, I need to talk to some people that have been smoking like 30, 40, 50 years is what I got to find. So I go out to the old folks home, the assisted living facility, whatever we're calling it these days, and I say, hey, I need to talk to some smokers. And so these smokers, they wheel them in there with their oxygen and their breathing apparatus and everything like this. And I get them all in a room and I say, oh, how many people here have smoked for 40 years? And some of them raise their hands. And I go, okay, anybody ever died from it? Nope, not me. Anybody here got lung cancer? No, Jim did, but he left last week, you know. So there you go. You say, nope, 40 years of smoking, no problems. Well, clearly the problem is that I've only talked to survivors. A lot of people have kind of fallen by the wayside. So what you really need to do, and what they've done to a good extent with mutual fund data now, is if you want 20 years of mutual fund data, you don't go find current mutual funds that have been around 20 years. Because those have been around 20 years because they had good results. If they had poor results, probabilities are they would have disappeared along the way. So then you're only looking at survivors, you're looking at a bias sample. And this is true with hedge funds too. Hedge funds have a very short average life. The ones that do well survive, the other ones implode, change their name, something changes about them because people take their money out and quit putting money in. Okay. So what you want to do is you want to go back 20 years ago. If you decided 20 years is the sample you need, you go back 20 years ago and say, okay, what were the existing mutual funds at that time? And then follow them through time for 20 years so that you don't have this survivorship bias. Look-ahead bias is if you're constructing a test, say some samples, say a portfolio selection criteria, and you're using that to form portfolios and see if you can beat the market. Well, one example of this is sometimes they'll form the portfolios on January 1 and see how they perform over the year. And maybe they'll form them based on their book-to-market ratios, the ratio of the book value per share to the market value per share at the beginning of the year. Well, this is fine. You're using year-end book values, but the fact is year-end financials don't come out till March or April. Various dates, but predominantly March or April. And so it's at that time that the financials are done, the accounting is out, and you actually know the book value. So if you're forming portfolios and testing them on January 1 based on information that wasn't even available till March or April, that's look-ahead bias. Because you couldn't have actually formed those portfolios in January, the data wasn't available. And the last one is time period bias. We may find a relationship that holds very strong over a 10-year period, but does that mean you want to bet money on it? Well, not exactly. If you look at another 10-year period and it just doesn't hold at all, or could be opposite, so something like the January effect turns into the January defect, you're going to lose your money. And so that's time period bias. You may find relationships that hold in certain time periods, but really just don't hold in other time periods. So those are the 5 types of bias. You should kind of know some of those buzzwords, and so you can differentiate between them, among them. Okay, well that brings us to the end of this reading. We'll get on to hypothesis testing in the next segment of quantitative methods.